which the cells originate in the ventral tegmental area and project to areas such as nucleus accumbens. Now, contrary to what you may have heard, nucleus accumbens is not the pleasure center of the brain. Dopamine is not the pleasure molecule. It's much, isn't that sad? It's much more complicated. Isn't that sad that things are complicated? I'm sorry. In fact, if you take food motivation, for example, what the literature shows, mesolimbic dopamine doesn't mediate the primary or unconditioned reinforcing or motivational properties of food, nor does it mediate the hedonic reactivity of food. Ken Barrett's going to talk a little bit about that. It's done a lot of that work. In fact, if you interfere with nucleus accumbens dopamine transmission, you get effects that are selective and dissociative in nature, impairing some aspects of motivation, but leaving other aspects intact. Okay. And a number of authors, including us, including Katz, have found various distinctions between aspects of motivation that are more dopamine dependent, and those of which are less dopamine dependent. What I'm going to talk about is this idea here, activational and directional aspects of motivation. It's an old idea in motivational theory that you have directional aspects of motivation, but you also have, of course, behavioral activation. Things like the vigor, persistence, or speed of work output, which is fundamental to aspects of motivation. For example, these processes enable organisms to overcome response costs or constraints that separate them from motivational relevant stimuli. Also, organisms continually make effort-related choices. I could be lounging at home watching TV in Connecticut, but I went through all the effort to come here to be with you folks. I'm very happy to do. Because this is a short talk, I'm going to take probably about 25 years worth of work and condense it to one slide so I can talk about the most recent stuff. So we've done a lot with just about everything you can do, dopamine, different types of dopamine antagonists, dopamine depletions, etc. If you interfere with nucleus accumbens dopamine transmission, what do you say? You reduce behavioral activation, so things like novelty-induced locomotion, schedule-induced activities, all right? And you suppress instrumental behaviors, but particularly those with high response requirements, high effort requirements. However, these manipulations leave intact the primary or unconditioned food reinforcement, food intake, and as I said before, hedonic reactivity to food. In addition, these manipulations alter effort-related decision-making and bias animals towards lower exertion of effort. So what do I mean by that? With effort-related decision-making, you give animals a choice. A larger or more valued reinforcer that they have to work harder for versus a smaller or less valued reinforcer that they don't have to work as hard for. Interference with accumbens dopamine transmission, what does it do? It shifts choice behavior, decreasing selection of the high effort option. However, the rats and mice for that matter, we've studied that, they show if they have impaired dopamine transmission, they're still directed towards the acquisition and consumption of food. So in the choice procedure, they exert less effort, they select lower cost alternatives. Now, the study of behavioral activation and effort, of course, has clinical implications as well. So you have symptoms such as psychomotor retardation, apathy, fatigue. You see all of these terms in the literature, anergia. They're core symptoms of depression, and we also see them in other disorders as well. A few points from the literature. Depressed patients, for example, show psychomotor impairments that actually resemble aspects of Parkinsonism. Depressed patients show reduced locomotor activity, and also energy or fatigue-related impairments that are correlated with the overall severity of depressive symptoms. In addition, our effort-related tests from animals have been translated to humans, and Treadway et al. Showed that depressed people show alterations in effort-related choice. And some of these ideas have been kicking around for a while. It's interesting when you look at the older literature. Klein, for example, noted years ago that depressed people can actually experience pleasure, but his quote was, you have to give it to them on a silver platter. Right? A few recent reviews, Treadway and Zoll, Pizzagalli, emphasize that many depressed patients have little impairment in what's now referred to as pleasure in the moment, the actual direct experience of the pleasurable stimulus. And so they refer to things like studies with the sweet taste test, where there are hedonic ratings of presented sweet solutions that actually in 4 separate studies, depressed patients don't differ from controls. And then another interesting thing that I really only got as I started to dig deeper into the clinical literature, I'm not a clinician myself, We always think of SSRIs as very popular treatments for depression. Turns out motivational symptoms such as inertia, fatigue are not well treated by SSRIs. And in fact, SSRIs can actually make these symptoms worse. So for that reason, what I've been doing just for the last few years is to develop explicit animal models of effort-related motivational dysfunction that may be applicable to depression but to other disorders as well. And we've looked at a bunch of things, and we're not going to present them all today. I'm going to mainly talk about some recent studies involving this agent here, tetrabenazine. So what is tetrabenazine? It's a drug that's commonly used now to treat Huntington's disease, but the side effects reported in the literature include fatigue, inertia, depression. What does tetrabenazine do? It blocks a protein called VMAT2, which basically enables neurotransmitter like dopamine to be stored in the storage vesicles. If you block that protein, the dopamine becomes depleted. Tetrabenazine also can deplete norepinephrine. However, the greatest effects are actually on dopamine in the striatal complex. And so here's a picture of a synapse. You couldn't escape without a synapse. Dopamine terminal here, just showing you there's a storage vesicle, normally stores dopamine so that it can later be released. VMAT2 is a protein on the vesicle that stores the dopamine. Tetrabenazine blocks that, and that results in a dopamine depletion. We've shown the dopamine depletion resulting from a low dose of tetrabenazine using a technique called microdialysis. We can actually look at extracellular dopamine in the brain. This is in nucleus accumbens, and you can see administration of tetrabenazine produces a substantial reduction of extracellular dopamine. So what are the behavioral effects on effort-related choice? Well, let's go through some of the tasks. And these are the same tasks that we've been using to study dopamine antagonists and other ways of depleting dopamine. So the first task, the concurrent fixed ratio 5 lever pressing. So what do you have here? Rats have a choice between lever pressing on a fixed ratio 5 schedule 5 times for one pellet. This is for a preferred pellet, high carbohydrate pellets, versus just simply approaching and consuming the regular lab chow. The rats strongly prefer those pellets. I agree with the rats. I've eaten both. I can't stand lab chow. They're not half bad. They're like something you get from a health food store or something like that. They're nutritionally balanced, but they're a little sweet. Okay. So the rats, under ordinary circumstances, lever press. They get most of their food, in fact, from lever pressing. But a dopamine depletion or dopamine antagonist shifts choice behavior. Lever pressing is reduced, but chow intake is actually increased. So here are the data with tetrabenazine. Tetrabenazine looks like a dopamine antagonist in terms of its effect. Dose-related decrease in lever pressing, but an increase, in chow intake. You get this effect if you inject the tetrabenazine directly into nucleus accumbens, which is shown there. That's these data here, decreased lever pressing, increased chow intake. But if you inject into a site in the dorsal striatum, you don't get that effect. So it shows it's site-specific. Now, if you ever do this type of behavioral study, what you know is that for every experiment you do, you have to do about 10 studies to show the meaning behind the first effect. And I'm not going to go through all of these things, but let me give you an example of ways that we've validated the effects of tetrabenazine. Tetrabenazine, though it decreases lever pressing for the carbohydrate pellets and increases chow intake, in free-feeding choice tests, it doesn't reduce food intake, and it doesn't change preference for the high carbohydrate pellets versus the chow. Okay? Also, in another study, we looked at sucrose intake, and preference for 5% sucrose over 0.3% sucrose is not affected by tetrabenazine. And then we read some of Kent's papers and used a measure of sucrose hedonic reactivity, a number of colleagues there, unaffected by these behaviorally active doses of tetrabenazine. All right, so another procedure we've used is the progressive ratio chow feeding task. So here, the rat lever presses for the preferred pellet, but the progressive ratio means they have to press more, and then more, and then more. Well, even though this rat knows the Olympic motto, apparently it eventually gives up. On this task, at some point, they stop lever pressing and they shift over to chow. So with this task, there's less lever pressing because the work requirement is harder and more challenging. What does tetrabenazine do? It decreases all the markers of lever pressing, but it does not decrease chow intake, and in fact, there's a trend towards an increase. In the animals with lower levels of baseline chow, there's actually a significant increase with tetrabenazine. Again, how do you validate this type of effect? You have to compare with other manipulations. We've compared with appetite suppressants. Appetite suppressants suppress both lever pressing and chow consumption, and so does pre-feeding. So pre-feeding to devalue the food reinforcement decreases lever pressing, but also decreases chow intake. That's what it looks like when you have lower food motivation or devalued food reinforcement. And then the last task is a really fun one, the T-maze choice task. So an animal has a choice between 4 pellets versus 2 pellets. How do we provide an effort-related challenge? Under some conditions, we have a vertical barrier, 44 centimeters. The rat with training learns to jump over the barrier to get the higher density of food. So here's the start arm here. You raise the start arm, and after all that training, the rat can use it for Rocky, and its head comes running out, throws itself to the top, flings itself over. So it exerts high degree of effort in order to get the higher density of food. And we've shown many times dopamine antagonists shift that choice behavior. So does tetrabenazine. So with this experiment, we looked at a few different conditions. So what if there's no barrier, and it's just 4 pellets in one arm and 2 in another? Tetrabenazine has no effect. That's the black bar. So the animals can discriminate between reinforcement magnitude and can tell the difference between left and right. What if there's 4 pellets in one arm, but none in the other one? So the only way the rat can get food is to climb the barrier. And again, that's the light gray bar. Tetrabenazine has no effect. It only has a significant effect on choice when there are 2 pellets in the arm without the barrier. So the animal shifts its choice behavior away from climbing the barrier, but towards the no barrier, the easy option. My grad students call that wimping out when the rat does that. They try to do an Arnold Schwarzenegger voice, but it doesn't quite get there. Okay, so now to summarize this phase of the talk, let's just go back over. Akuma's dopamine depletion, dopamine antagonism we showed before. They lead rat to exert less physical effort and select lower choice alternatives. These effects don't resemble reinforcer devaluation by pre-feeding. They don't resemble the effects of appetite suppressants. I didn't show that, but we published that. In addition, as a summary, these effects, they don't seem to be due to changes in appetite, food consumption, food preference, discrimination of reward magnitude, or reference memory. So now, another part of this, why develop an animal model? One of the reasons, or you can see if there are drug treatments that reverse the effects of tetrabenazine. So we've been looking at that. And one thing we've been looking at is adenosine antagonist. Here we go, we got our coffee here. So caffeine, which makes you do stupid things faster, but more energy, there you go, is a non-selective adenosine antagonist. In the brain, the major ones, the major adenosine receptors are A1 and A2A. And what we've been focusing on is specifically the A2A receptor. Why? Because it's highly concentrated in the dopamine-rich regions of the striatal complex, both caudocutaneous and nucleus accumbens. This is the rat, and the same thing is true of humans. So there's a lot of interest in drugs that are selective adenosine A2A antagonists. Why? They're being studied for potential anti-Parkinsonian effects, and in fact, one, istradefylline, is actually used in Japan for that purpose. They're also being assessed for antidepressant effects. And we've published a number of papers showing that adenosine A2A antagonists reverse the effort-related effects of dopamine D2 antagonists, probably because these receptors are actually co-localized on the same cells in the striatal complex. So what about tetrabenazine? We've done a whole bunch of reversal studies. So here's what we did. We showed the effect of tetrabenazine. So this is the FR5 choice procedure. What does tetrabenazine do? It decreases lever pressing, but increases challenge. Co-administration of an adenosine A2A antagonist, MSX3, this comes from Christa Mueller's lab in Germany. It restores the normal pattern of behavior, increases lever pressing, and decreases chow intake in tetrabenazine treated animals. What about the progressive ratio choice procedure? We see the same thing. Again, you have the decrease in markers of lever pressing with tetrabenazine. Co-administration with MSX3 restores the normal pattern of behavior, increasing markers of lever pressing, but neither manipulation has an effect on challenge. And then with the TMAs, what's the effect of tetrabenazine? As we saw before, it decreases selection of the high barrier arm. Co-administration with the adenosine A2A antagonist restores the normal pattern of behavior, increasing selection of the high effort, the high barrier arm. All right, so another thing we started looking at, of course, many of the classic antidepressants are what? They're monoamine uptake inhibitors. So we've started to look at those drugs. So we've looked at, for example, bupropion, Wellbutrin, which is a catecholamine uptake inhibitor, so it does inhibit dopamine transport. We've also looked at an experimental drug, GBR12909, which is a selective dopamine uptake inhibitor. And what did we show? These two drugs both reverse the effects of tetrabenazine. So here, bupropion. Tetrabenazine decreases lever pressing, increases chow intake. Bupropion co-administration increases lever pressing and decreases chow intake in the tetrabenazine-treated animals. So it at least partially reverses the effects of tetrabenazine. What about GBR12909? It does the same thing. So tetrabenazine decreases lever pressing, increases chow intake. Co-administration with the selective dopamine uptake inhibitor increases lever pressing and decreases chow intake, restoring the normal pattern of behavior. What about SSRIs? They don't do that. What about a selective norepinephrine uptake inhibitor? It doesn't. It's interesting. So here's fluoxetine, Prozac. Co-administration with tetrabenazine doesn't increase lever pressing, in fact produces a further decrease in lever pressing and also a decrease in chow intake. Dazipramine is a selective norepinephrine uptake blocker, and again, it does not reverse the effects. So this seems to reflect a dopaminergic component to this aspect of motivational response. All right, so just as a brief summary, the adenosine A2A antagonist, the dopamine uptake inhibitor, reverse the effects of tetrabenazine. In contrast, for example, Prozac does not, but there are clinical studies, as I said before, that suggest that SSRIs are relatively poor at treating this type of motivational impairment in humans. Right, and then one last thing. What about individual differences? A lot of times we always treat like we assume all rats are the same. They're not. They're very different. And the task that brings out the effort-related differences quite strongly is that progressive ratio choice task. So some animals are very high responders, some very low responders. And that relates to things like dopamine signaling and differences in drug response. So in this particular study, ran with all 2012, we took a whole very large group of animals and we did a median split, and we had groups that we called workers versus slackers. My students started off calling them winners and losers, but I thought if a rat would be stigmatized by being called a loser, we didn't want to do that. So here's the range. Look at the range of the workers. Huge, 205 to 2,800. The slackers down here, very low lever pressing. It turns out this difference was related to a difference in dopamine neurochemistry. So phosphorylated DART 32 is phosphorylated at what's called the threonine 34 site. That's a marker of the cellular response to dopamine. Not dopamine release per se, but when the dopamine is detected by the postsynaptic cell, how does it respond? A signal transduction response. And as you can see here, in the nucleus accumbens core, there's a significant difference. The high responders have higher dopamine-related signal transduction activity. In another region of the nucleus accumbens, there was a trend towards that, but it wasn't statistically significant. And we also see interesting things when we give a drug that increases dopamine transmission. So bupropion, again, catecholamine uptake inhibitor, increases progressive ratio responding across dose. So there's no tetrabenazine on board. We just take our winners and our losers, we give them bupropion, and you can see increases in responding. So you can increase the lever pressing output. And what's interesting, look at our losers. They're lower significantly here, here, and here. But at the highest dose, they don't differ anymore from from the high responders. So the administration of bupropion is able to turn basically slackers into workers, to go with the terminology we use today. What other drugs do that? GBR increases output, and also MSX3. Drugs that don't increase prog output and actually decrease it, again, fluoxetine, Prozac, and dizipramine, norepinephrine uptake inhibitor. So, conclusion. Akuma's dopamine transmission seems to be critical for effort-related decision-making. There's a bidirectional modulation of effort-related choice by dopamine-related manipulation. So reduced dopamine transmission biases animals towards low-effort expenditure, but enhanced dopamine transmission increases selection of high-effort alternatives. And this is a bit like the triple et al. Paper that you're a co-author on, with the increase in dopamine transmission in nucleus accumbens showing this effect. And we also have single transduction studies showing increased dopamine activity with effort-related challenges. All right? Now, dopamine doesn't act alone. No neurotransmitter does. Of course, it interacts with other transmitters. And we think that these preclinical studies in animals are potentially relevant for understanding effort-related dysfunction in humans. And we think, to a certain extent, what we've done is identified a dopaminergic component of an important aspect of motivation that may be highly relevant for understanding the symptoms of depression, but also other disorders in which there are motivational impairments as well. Thank you very much.